Hello, everyone. It's my great pleasure to introduce Dr. Aisha Urooj, who is a research fellow at Machine Intelligence in Medical Imaging Lab, Mayo Clinic. She received her PhD from the Center for Research in Computer Vision at the University of Central Florida, where she was advised by Dr. Mubarak Shah and Dr. Hilde Vitoria Lobo. She also worked at MIT IBM Watson AI Lab as a research scientist intern in summers 2020 and 2021. Her research interests include multimodal understanding tasks involving language and vision, with a focus on representation learning, visual question answering, and visual grounding. So with this brief introduction, I would like to welcome Dr. Urooj one more time. The floor is yours.
Thank you, Dr. Amini, for the introduction. So today I'm going to talk about our recent work, which is learning situation hypergraphs for video question answering. And I will dive right into this. Interesting. Okay. So I will first just give a brief introduction of the problem we want to solve here. So visual question answering is a multimodal understanding task where you need the understanding of both visual world, which can be an image or a video, and the natural language to solve this task. So in visual question answering, you are given an image. Let me just you are given an image and a natural language question, and the task is to answer this question. For example, in this image, the question is, are the black horses to the right of the vehicle on the road? And if you look at this image, we can see that the black horses are on the right of this vehicle. So the answer is yes. Now, in video question answering, you are given a video which will have certain actions happening in this. And again, you are given a natural language question about that. So here the question is, what did they hold before opening the closet? And to come up with this answer, we have to look at the full video, and we can see here the correct answer was phone. So visual question answering task has many challenges. One of the main challenge with this task is that often we do not have the information present in the image which is being asked, which the question is asking about. Here are some situations. For example, in this image, we have some situation and the question is it raining heavily? And the answer is yes. Although we cannot see the rain here, but looking at the people who are wearing, holding umbrellas, we can say, yes, it is raining. And so to answer this question, we need to use common sense. Here is another example. The question is, are there an equal number of large things and metal spheres? And the correct answer is yes. So to answer it correctly, we need to understand the notion of what does it mean by large things. So, and then we have to count the number of large things. And then metal sphere. So we have to understand what does a sphere look like and what is the material, like what does metal means, and then count, and then we can come up with the right answer. So to solve this task, we need to do, it comes under the visual reasoning notion. Then there is another example. The question is, what phylum does this animal belong to? And the answer is chordate or chordata. To answer this question, we need to make use of an outside knowledge. Then another challenge we face with VQA is that a simple phrase in language may take many visual representations. For example, here I Googled this simple phrase, a blue bag, and on Google, I could see all kind of shapes and varieties of blue bags. So which makes this task very difficult. Because when we are training a model, we need data, and if you show a certain kind of blue bags, and then at test time, you are showing a different kind of blue bag, then the model may struggle. When we extend this visual question answering task to the videos, then it becomes even more complex, because now we not only have to understand a situation, we also have to understand the fine-grained details in a video, and we have to do the reasoning in the space as well as the time dimension. We also have to understand the question will be more complex now, and we have to understand the fine-grained question semantics. We will see more examples in next slides to understand what does it mean. And to solve the video question answering task, we need many more reasoning capabilities than solving image question answering task. For example, we have to understand the actions, we have to understand the interactions happening between different objects over time. We have to understand the notion of sequence of events, like which event happened first, which event happened after that. And a question could be about some situation in the video, right? So we have to localize those relevant moments which are related to the question within a clip. And if the question can not only be about video, so this is a special case where a question could be about some part of the video and some part of the dialogue happening between different people. So if that's the case, then we have to understand the other modalities as well. Like we have to understand the video, we have to understand the audio or subtitles, which is then becomes a language thing. So here is an example. So we are given this video. And for this video, we are shown these questions. The question is, what did the person hold after putting a phone somewhere? And the answer is bottle. So to come up with this answer, we have to, a system first have to understand what does an action hold means, and what does this action means putting a phone somewhere, and then it has to understand that we are asking about something which is happening, like this action should happen after this action. Here is another example. So the question is, were they taking a picture or holding a bottle for longer? And here we see that, okay, the picture was being taken in first 2 frames, and then the bottle the person was holding for a longer period. So we have to not only recognize these actions happening in the video, we also have to understand the duration, that, okay, which action happened for longer. So which makes it much more complex than simple visual question answering task. But if we understand what are the actions happening in a video and what is the relationship between different objects over time, that makes our job much easier. Here, I can show how. So we have this video frame. Here, a person is picking up phone. Then here, the action changes to taking a picture, which means the relation between person and the other object, which is phone here, changes. And similarly, we have the different actions happening here, putting a phone down. And if the person is putting a phone down, then the relation of person with object is varying now over time. And then in the last frames, the action was holding a bottle. The relation is with the bottle, but like to hold a bottle, she's doing different actions like twisting. Then person is behind bottle, and then person is on left of bottle. This is why they say, okay, here it was holding, but maybe if we go further in over time, it will be like putting down bottle. But if we have this spatio-temporal scene graph, if we know this, then the answering the question becomes much easier. Now, if you look at this same question again, what did the person hold after putting a phone somewhere? Given this spatio-temporal scene graph, we will know, okay, this is the action, putting a phone down. The next action was holding something, and the relation between person and some object of which is named hold is with this object bottle. So we can say, okay, the answer is bottle. So to solve this problem, this is the work which we did, and it is published in, it is accepted in CVPR 2023 with my amazing collaborators from MIT, IPM, and with my advisors. So I will dive into this thing. So first thing is the title says Learning Situation Hypergraph for Video Question Answering. So what is a situation hypergraph here? A situation hypergraph is a concept very similar to what I have shown in the previous slide. So we are given a video, and in this video, in the first frame, we have some situation, and that situation is between person and some objects. So a person, she has many objects in front of her, but she can have, with each object, she will have some relation, so which represents a situation. So let's say for this frame, the situation was person in front of bottle, person holding bottle. So we have different entities and we have different relations between these entities. Then in the next frame, the relations changes and the entities, more entities may add more and some entities may remove from the next situation. So here like person, bottle on table, person in front of table, and so on and so forth. So now these situations may change over time. So at each time step, we have a certain situation. And for that situation, we have some actions, we call them atomic actions happening in that situation, like touching or holding. But these situations can be connected by an action which may comprise of multiple situations. Like here, for these first two frames, the action is putting down a bottle somewhere. So this action is considered an hyper edge, which is connecting the situation graphs of two situations which we see here. So similarly, we have another action holding a phone, which is comprised of these four situations. So this is what situation hypergraph look like. And the objective of our work here is that we want to learn the situation hypergraph to solve this video question answering task. So how do we do that? Here is our approach. We take a video and we pass it through a backbone network, which is a neural network. It gives us video features. These video features are 3D convolutional features. We flatten them to construct video tokens, and we append a special class token with it, which call it Viz. And then with these tokens, we add the position embedding and pass it through a visual transformer network. So now this transformer encoder gives us the encoded video features here. On the language part, we have this question here for this given video, we have the question, what did the person do with the bottle? And the question can be in two setups. Here we are seeing multiple choices. So usually VQA tasks can be solved in either open-ended setup, where you are given simply a question and you are asked to come up with the answer, or you could be given multiple choices and your task is to pick the right choice. So either way, you take either the question and the multiple choices or simply the question and pass it through a text encoder. Here we are taking a transformer encoder. So we tokenize these into words and then we append a special class token with it. And then this is passed through a transformer encoder to get the encoded question words. Now, once we have these embedded or encoded visual word tokens and question tokens, we take these video tokens and we construct a situation hypergraph out of this. So given this, let's say this yellow block is giving us situation hypergraph embeddings here. Now these, so usually the previous words, what they do is they take the visual features and they take the question features and they use the cross attention, some kind of attention between them, some kind of interaction between them to solve the task. Now, instead of doing cross attention between directly video features and the question features, we want to do interaction between situation hypergraph tokens and questions. So for that purpose, we take the hypergraph embeddings here, we take the question features here, and we use the cross-attentional transformer, which is using attention between graph tokens and which are coming out of the video and the question tokens or features to give us some output features. Now, the output features which are coming out of this cross-attentional module will have information both from the situation hypergraph as well as the question. Those features are passed through an MLP to predict the right answer. Now, the question is how we are learning the situation hypergraph embeddings. So for that purpose, we take this action decoder. This action decoder is taking video tokens. And it has these trainable action queries. So it is taking some queries which are passed to this action decoder. It is taking video tokens as context, which means that the query and values are coming from here. And then it gives us some decoded features for actions. Now, these features are passed through a prediction head, which the task or the goal of this prediction head is to predict which actions are happening in the video. So it takes the video. If we simplify it, we are taking a video and we want to predict which actions are happening at each step. And it gives us some predictions over here. We have some we know what actual labels were what actual actions were happening, at least at training time. So at training time, we know which actions were happening. We compute the loss. I will go into details later on, but we compute the loss between the predicted actions and the ground truth actions. Similarly, we take some queries for relationship, which we want to learn. We take the video tokens for this decoder, and this decoder gives us decoded relationship queries. We pass these queries features to a prediction head, which gives us the relationship, which predicts the relations between different objects, between person and different objects at each time step. And again, we have a loss to learn these relationships. Now, once we have predicted the once we have learned to predict the relations as well as actions from the given video, we take these decoded features and construct a situation hypergraph out of these decoded features. So how we are computing the loss, excuse me. So we have, let's say we have these decoded queries coming out of a decoder. Here we are taking the example of action decoder. So these decoded queries are passed through a classifier, which is a feed-forward network. And then this classifier predicts an action. So for this decoded query, let's say it predicted book on table. For next two decoded queries, it predicted no class, because we have to give this option to the, because each video is can be different, and we do not know how many actions were happening at each in each video. So we have to give an option that there is a possibility that no action is happening. So we have this like these decoded queries are predicted into no class, and then for the next one, the classifier predicted that there was person holding bottle, and then next one was person in front of bottle, in front of table. So these were the predicted classes. And then we have a set of ground truth labels, which was person holding bottle and person in front of table. So we want to do a matching between them, which should be optimal. And by optimal, we mean the matching which gives us the best output. And to get that best output, we assign a cost. For each matched pair, we have some cost. So what we want to do is we want to minimize the total cost of this matching. When we want to do a pairwise matching, the number of elements in both sets should be equal. So we have append this no class token here as well. So first thing is to find optimal matching. And once we have find this optimal matching, by optimal matching, we mean the matching which has a minimum cost. We compute the loss for the matching pairs. And so how are we computing this optimal matching? It is a standard. The concept comes from a standard bipartite matching function. So in optimal bipartite matching, let's say if we are matching n elements, so we take a permutation of these n elements, which is sigma here. And then we have a function, a matching function, which takes the ith ground truth label, yi, and then y hat sub sigma sub I is the predicted label at ith index for this permutation. So we can have, for n elements, we can have many permutations. For each permutation, we will compute this matching cost. We want to, and then the matching cost is summed for over all elements. And what we want to do is we want to find a matching between these two sets of n elements, which gives us the minimum cost. So we extend, and this L match is the pairwise matching cost function. So we extend this idea to the videos by a very simple thing. We do not do anything fancy here. What is this? Again, now when we extend it to videos, which it means that we are extending it to time dimension. So we are predicting n elements at each time step. So what we want to do is for each time step t, we take a permutation of n elements at that time step. And for this permutation, we are computing the matching cost between the ith ground truth action for that time step and the predicted action at ith index for permutation at that time. And the matching cost function will be this, where we have to make sure that the class label is not equal to the no class label, like that, because that was a dummy label we added. And the matching cost function, it will be taking into account the cost will be the predicted probability cost of that class. And then we do the same thing over all time steps. So the total cost will be summed over all time steps for the video. So once we have found the optimal matching like this, we then compute a simple cross entropy loss for the full video with the class labels. So this is how the loss function looks like for predicting actions. It's very similar, exactly the same actually for relationship. The only thing which is different here is that now we are computing the cost for the set of relationships. And we have M relationships here again. So we have a permutation of M elements at time step T. And we take this ith ground truth relationship, compute the matching cost with the predicted relation at that index for permutation sigma T. And once we have found this optimal matching for the full video, we compute the cross entropy loss between the class labels as well as the predicted labels. So once we have, okay, so this is how we were computing the losses for actions and relationships. Now, once we have predicted the situation hypergraph embeddings, how we are in constructing the embeddings out of those, like what other information is going in there to the cross-attention transformer, that information is here. So we are given this action queries. Again, we have this action decoder. It gave us some decoded action queries. Similarly, we had this relationship decoder. It gave us some decoded relationship queries. Now for situation T, we have N action tokens and we have M relation tokens. Now these are the decoded queries we had, which are coming like these decoded queries simply as this. If the decoded queries are less than like this, means that you had some actual queries, but it predicted like here, this decoded query, sorry, not for this decoded query. In actual, so we have N action tokens, but in actual, this token, we do not have anything here in ground truth. But here, let's say we have M relationships. Now the information we add or with these decoded queries is as follows. So first thing we add is the type encoding, because now we want to tell which tokens belong to the action and which tokens belong to relationships. So we have a type encoding, simply act for actions, and then this special token will be added for relations so that we can distinguish between, the system can distinguish between them. We also add an attention mask here. So for actual actions or for actual relationships, the mask will be 1, otherwise it will be 0. This is only at training time. At test time, we assume that we do not know, we do not have any information about the graph. So what we do is we take the attention mask as 1. And then we also add the situation ID, which tells us that at which time step we are. So if we are at situation T, we will add this information over here. Once we have this information, these all will be summed together to give us the situation hypergraph embeddings for each situation. We concatenate a special token. This here we name it edgy. The concept of this token is exactly the same like we have a class token in language models, language transformers, where the task is to actually aggregate the information from all fine-grained tokens. So now this is how the situation hypergraph embeddings are being constructed, and then this is fed into the cross-attention transformer with the question for the rest of the processing. So the training objective in our case will be, once we had a VQA loss, but along with this VQA loss, we have a loss over predicting actions and a loss for relationships. And we sum these together to get the total loss. So to train this system, we consider 2 data sets. first was Action Genome QA dataset. So in Action Genome QA, we have 2.27 million question answer pairs over charades. Charades is a video action dataset. Yeah. And this dataset has 3 novel challenges. So first is indirect references. I will go into the details in the later slide. Indirect references. Second challenge is novel compositions. And then third one is more compositional steps. So here is how the challenges look like. So first challenge is the novel compositions. For this, for example, here we are taking to understand this novel composition, we are taking 2 discrete ideas, before and standing up. So at training time, for instance, you have seen before and standing up with different concepts, with other concepts, like before was seen with washing a dish, lying down, throwing it on the table. And similarly, standing up was seen with some other concepts, but both of them were never seen together at training time. But at test time, we combine these together in a question and see if the model was able to understand these 2 concepts separately. And even if we show a novel composition of different concepts which were seen separately, whether the system is able to answer the question correctly or not. Then the second challenge is indirect references. For indirect references, the concept is very simple. You could ask a direct question. For example, here the direct reference is, did the person twist the bottle? And then an indirect reference could be to that same object could be, did the person twist the object they were holding last? So again, we are referring to the bottle here, but now we are referring in an indirect way. So if a system, if a model has understood this concept that what does a bottle look like, how the twisting action is happening. So if it has learned to answer the question in a direct manner, it should be able to answer the question in an indirect manner as well. Then the third challenge is more novel compositions, where you could show if a system, where we test basically that if a system has understood the complex reasoning steps or not. So what you do is you train a system with very less number of reasoning steps, and then at test time you are showing a question which is much more complex and which requires many more reasoning steps to come up with the right answer. So here, let's say here is an example. The question is, what did they touch last before holding the bottle and after taking a picture, a phone or a bottle? So each colored word here is basically a composition. And to come up with the right answer for this question, we have to understand, like generalize to 1, 2, 3, 4, 5, around at least 6 compositional steps are required to answer this question. So and now I'm going to show the results on this AGQA benchmark. Here we are showing this question type, if it is a reasoning based, whether the reasoning is between object and relationship for action, object action. The question is about superlative, sequencing, existing question, and so on and so forth. So these were the baselines, and they have some specific performance for ease reasoning type. Then here are the results which we obtained from our method. The question could be based on the semantics. Let's say if the question is about object, if the question is about relationships, if a question is being asked about certain action. And again, when we are learning the situation hypergraph, it gives us advantage over the baseline systems. And the question could be about the question type could be sorted based on the structure of the question. Like if the question was about simple query question, or if the question was asking to compare 2 discrete ideas, if the question was asking to choose between 2 concepts, or if there was some logic, or whether the question was about verifying something, which means a yes or no question. So we see a clear advantage of learning this graph over the baseline methods. And then we could split all questions based on the binary questions. Binary means that the answer to the question will be either yes or no. Again, open-ended question is where you simply ask a question and the answer could be anything. And overall, we saw a significant gain. For this challenge of more compositional steps, where you were shown, okay, so here for the novel compositions, the concept where we are saying that there are two different concepts which were never seen during the training, we see that we had a better performance. The open-ended questions were more challenging for the novel compositions compared to the binary questions. Then another benchmark on which we validated our system was STAR benchmark. So STAR benchmark is also about situated reasoning in real world videos. And this benchmark is also based on the videos from charades. They provided 60,000 question answer pairs with 4 question types. First is interaction, sequence, prediction, and feasibility. And here is an example. So you have some precondition, which could be a situation, and then the time, with the progression of time, the situation changes, and you have some part, you might be shown some part of the video, and then you will have some unseen part of the video. And the questions could look like this. So here an interaction question is, what did the person do with the bottle? So an interaction question is where we are asking about some interaction between person and some object. And you are given, for STAR benchmark, we are given the multiple choices setup. So we have to pick the right choice. A sequence question could look like this. What object did the person take after the person put down the bottle? So this is a question where we are talking about some sequence of events, and then a question could be about anything. So here, let's say the question was about some object which person took. So this was first event, and then after person put down the bottle. The next thing, third type is prediction. So this is the future prediction task. So a question could be about, you are shown some part of the video which we saw here, and then the question could be about the future, something which will happen in the future. So this is a complex question. And then feasibility questions are also a complex question type, where you are shown some part of the video, and the question is asking about what action is or what step is feasible to be taken next. So here, let's say the question is, which object is possible to be took when the person is in front of the table? And then you are shown some objects, and given the situation, we have to see which action is most feasible. For instance, if there are some elephant in front of this person, and if the question was which object is possible we took, and there was some choice with elephant, we know that a person can never pick up an elephant. So this is based on the feasibility. So again, based on when we evaluated our system on this benchmark, we saw our system was able to, overall we had some good performance, but we see here that the prediction feasibility are the most challenging question types. Interaction was is relatively easiest, still there is much room for improvement, but still we saw overall that the interaction was the easiest question type. Then we did some ablations to validate our system. First thing was to investigate how much the quality of these hypergraphs impact the system. So to do that, so what we did is we took the ground truth hypergraphs and took the questions and learned a system which is taking the ground truth hypergraphs to come up with the right answer. And we found that if we are able to predict the hypergraphs correctly, it significantly improves the performance compared to the predicted hypergraphs. So yeah, the quality of hypergraphs is important. We also tried different combinations of doing cross attention between the question and vision modality. So first thing was this was our final choice. We were taking the hypergraphs with the question. We could also take the hypergraphs as well as the video as well as with the question. But we saw no significant gain. Actually, just using the hypergraph gave us slightly better performance. Then we also tried different training protocols. This is, I think, not very important for this talk. Yeah, we can skip this. Another ablation study we did was based on the hypergraph components, whether do we really need to learn both action relationship, or we could just do well with either of them. So here we tried a model where we're only predicting actions, or we are only predicting relationships, and when we are predicting both actions and relationships. So these numbers are the number of actions, number of queries we were taking. So 3 means that we are taking 3 queries per time step. So for each video frame, we want to predict 3 actions. Here 8 means we want to predict 8 relationships per time step. And also we experiment with number of queries, like how many queries should we really take. And we saw that predicting 3 actions per frame and 12 relationships per frame gave us better performance. We also evaluated the quality of predicted hypergraphs, like how well our system was able to learn these hypergraphs, and we saw that it was doing decent job. Overall, in terms of mean average precision, we got 87.63 mean average precision for action prediction and around 73% for relationships. Okay, so some a couple of takeaway from this work was that learning situation hypergraphs is data efficient, and we found that by because the AGQ dataset, it had around 1 million question answer pairs. So we started with a small scale experiment where we took only 100,000 questions from this dataset and trained our system. And we found that even with 100,000 questions, we were able to outperform the baselines. And when we take the full training set, we were able to perform much more better. So if we can learn this notion of the underlying semantics of the video, that means that we are understanding what's happening in the video, and it is going to help us a lot. And we do not need a lot more data if we understand the concepts really well. Then it can help us with, even with a small set, we can do really well for a video understanding task. We also try to test the correlation between accuracy and compositional steps. For that, we fit a linear regression model. And here I'm showing graphs based on for the binary questions as well as the open questions. And we see that for the binary questions, increasing number of compositional steps actually makes the question more challenging compared to when the question is open-ended. Increasing for the open-ended questions, if the question is open-ended and being asked in less compositional steps, then the models are struggling more compared to when you are giving more conditions in the question in an open-ended questions, which makes this like my takeaway from it was that when we are asking an open-ended question and we are clarifying it more, like we are giving more and more reasoning, what should I say, cues in the question, then it becomes slightly easier for the models to predict the answer. But overall, still the human's performance is very consistent for compositional steps where the models are struggling. So there is still a huge gap for improvement. So to summarize this talk, we proposed a system which was learning the underlying situation hypergraph, and it shows that learning these situation hypergraphs are crucial for complex video understanding tasks. It may lead to data efficiency for neural networks, but it has its own challenges. Like we are using the annotated graphs to learn this system. At inference time, we do not need these annotations, but at test time, at training time, we need some annotations. So that is one limitation, also, which actually also leads to another limitation, which is scalability. So if we could find some self-supervised ways to learn these graphs, and this is very much possible. So that will elevate the limitation of data annotations, and it will help us in scaling these systems, and which will enable us to solve many more complex understanding tasks. Yeah, so that's all from my side. Thank you so much for listening, and I'm open for any questions.
Thank you, Dr. Urooj. It was a very insightful